So this is my Module 3 presentation. And so I use SPSS. Gotta admit, it's pretty shitty, but I did the best of what I could as far as the plots and the diagnostics. All right, so MRC, multiple regression and correlation. We're looking at associations. This is a standard formula. Gives us a line of best fit. That gives us the smallest squared residuals, meaning that the residuals are as close to the line as possible. It tells us how multiple independent variables impact the criterion, which is the outcome, and the errors are attributed to the model. So for my for these purposes, I use y1, x1, x2, and x3. Here's some descriptive statistics. The unstandardized b values are slope, and it's basically how much a change of one in the independent variable changes the dependent variable. The t's are indicators of how beta is different from zero. It's inversely related to the significance or the p-value. We want standard error to be low, so there's low variability about the betas. So these are some assumptions for the MRC. So these are pretty self-explanatory. The third one is independence of results. So for my diagnostics, it gave me the Darwin-Watson, and it said that a value of 2 indicates that the residuals are independent. So it's very close to 2 there. So I assume that that assumption is not violated. The next one is the linear relationships between the residuals and the dependent variables. This seems to be linear. It's not that great of a relationship, but I don't think it violates. To further that, I included the partial correlations because that's important. So this is just another view of the relationship between the residuals and the dependent variables. The fifth assumption is homoscedasticity of residuals, and that's basically looking at the variance around the regression, making sure it's constant for the predicted variables. I would say that this area right here is problematic, but once again, SPSS, the diagnostics weren't that great, so I didn't get the nice R chart, but I think this is okay. The sixth assumption, and probably one of the most important, is you don't want any collinearity. And so basically what I found was X1 and X3, they have a pretty high correlation. But since that's the only one, it might be attributed to the fact that, like the more variables you include, the higher the chance that you have correlation amongst the variables. So what I did to check that was looked at the variance inflation factor, and a value of 1 indicates that there isn't collinearity, and these values are right around that. So I don't believe that collinearity is a problem for this data set. As we learned from the Cortina article, collinearity is like a very important factor for multiple regression because like high collinearity can inflate the beta and the standard errors, which basically tarnishes our like best guess about the data that we're looking at, which is never good because we always want to be as precise as possible. The next one is outliers and leverage / influential points. Once again, this is the output I got when I ran my diagnostics. So we're looking at Cook's distance and the centered leverage. So Cook's, this 0.9 value right here is the highest, which is close to 1. So that's obviously problematic. But then when you look at the average, it's only 0.063. So I would say overall it's fine. No graph is provided because SPSS sets the threshold for plus or minus 3 standard deviations as far as residuals. So I didn't have anything to go on off of that other than looking at that one high point compared to the average. Then the eighth one, the normal distribution of residuals. So they actually gave me a pretty nice output here. As you can see, the data looks pretty good. You know, it would be better if this one was right here, but it's right around the center, so I'll take that. Then we look at the PP plot of the expected or y-hat value versus the observed values, and you can see that the data hugs the line very nicely. You know, it's a good mix of above and below. So we got that least squares going on right there. So I say that does not violate that eighth assumption. So what does this tell us? So using the variables, I got the equation y equals negative 0.087, which is the y-intercept, plus 0.306x minus 0.052x plus 0.196. So basically what that did was, you know, it took these unstandardized beta values and it basically, the equation is, we're using this model to predict future dependent variables based on those input variables. So the betas are the input variables that basically are the key to the formula as far as predicting out other values. The equation is the parameter estimate because we aim to use it in relation to the population. So the overall goal of, you know, doing these things is not just for the sample, but it's like how telling the sample is in relation to the population. So that's why we had to make sure that those assumptions weren't violated, or as few assumptions were violated as possible, because we want to be able to use our model in relation to the population. The R squared value is of importance also because right there, 0.344, that value isn't that high, but what it tells you is that basically 34% of the variation in the dependent variable is explained by the independent variable. So obviously we would like that to be as close to 1 so we can be confident in our models saying that when we change the independent variable, the dependent variable will react accordingly. Gary King stressed that when we do multiple regression, it's very important that we analyze all the independent variables with the dependent variable simultaneously so that we can accurately measure how like all of the independent variables that we're looking at impact the dependent variable at the same time. Because most of the time when we're like doing this, we are looking at variables that, you know, you can't tease apart. Like, you know, there are multiple factors that lead to intelligence and you can't like really control for one at a time. So you just have to do them all simultaneously to get like the full picture of what's going on. So for ANOVA, this is the second branch of the general linear model. It's a measure of difference between multiple means, and it's basically a ratio of signal to noise, or sum of squares divided by degrees of freedom. And in this one, the errors are attributed to the user. Differences, you know, MRC is association, ANOVA is differences. We can actually switch between the two by using the point by serial formula, which I won't get into. But the ANOVA is more strict, and that's because there are a few more moving parts, you know, which I'll get into in a second. But they both are used to compare the influence of multiple independent variables on a dependent variable. So for my data, I tried to make a story with it. So I used factor 4, factor 5, and Y1. I changed factor 4 to political affiliation, 5 to race between black and white, and then Y1 was just the outcome. So there goes some values. So the main effects and interactions. So basically with this test, the null hypothesis is that the mean between the differences is going to be 0. So there's not going to be a difference between black and white or the political parties. And so I use the type 3 sums of squares because I figured there wouldn't be any interaction among the variables, so I wouldn't need to like, you know, tease apart what was causing the variation or the variance in the model. And I also didn't use a post hoc because there were no significant findings as evidenced by the relatively low F scores and the accordingly high significant values All right, so this is just another, example of how the data really, there's no significant findings from it as far as interactions or effects. So there are a series of assumptions too. These very self-explanatory, continuous dependent variable, two independent categorical variables, and independent observations. So it didn't produce the Levers versus Cook's distance plot, but as you can see here, it does indicate that participant 6 is an outlier, and so that could affect the data as far as violating this assumption. So moving on to the next one, normal distribution of the residuals. So for my residual, or for my diagnostics, it gave me the Shapiro-Wick test, which for that test, the null hypothesis is that the values are normally distributed. So failing to reject the null means that the values aren't significantly different. So basically, based on these values right here, that one's close, but that doesn't matter. There's no reason to reject the null, so there is normal distribution of residuals. And here's just a plot. I wish I knew how to use R because they would have been together, but you can see the lines and the values, nothing really jumps out at me. That one's a little problematic, but once again, there were no significant findings, so I don't have a reason to reject or to assume that I violated the assumption. The last one, homogeneity of variances. So it gave me the Leibniz test of equality of error variances, and right there is a little handy, what exactly that says. So we have an F of 1.057. Degrees of freedom come from, I had, a 2x2, so that would be 4, and the degrees of freedom is obviously going to be 3. Then 26 comes from the fact that there are 30 observations, which worked out nicely because it was a balanced design, 15 and 15. But overall, I failed to reject the null hypothesis, so I can assume that there is homogeneity of variances. So what does this all mean? So for my example, race and political preference have no impact on income, which you can see like right here, like nothing changed, like these confidence intervals overlap, so there's no significant like difference, like being black or being like nothing made you earn less or more. So just to recap, we use ANOVA to test the differences of means for different treatments or the different groups. To tie it into the population parameters, our estimates are for the population once again, and that's just why we check these estimates. So overall, general linear model is definitely very useful because it allows us, a little bit of flexibility depending on what we're looking at in terms of multiple independent variables. It's a really good tool because when we identify what we need to look at, we have 2 clear routes to use, and the tool is only as good as the person using it. So we need to make sure that we understand what we're doing before we try to use these models and make inferences about the population that could impact someone else's life.